Topic 7.2, Basics of Policy Evaluation. So frequently, we implement a policy, a program, or intervention, and then we are interested to understand the causal effect of this policy, this program, these interventions. An example would be, suppose that state government decided to limit the class size to no more than 20 in high school. So hoping to improve the students' performance. However, does this policy improve students' performance or not? We need to evaluate this. Evaluate the effect of this policy. Or a fertilizer manufacturing firms launch a new variety of fertilizers. How effective is this new fertilizers in improving the yields? So we can evaluate this fertilizer intervention in a sense. Okay, to answer these questions, we can use the potential outcome framework, or this is Lubin's causal models. So here it's important for us to distinguish two concepts, causality and correlation. What do we mean by causality? If we say X cause Y, that means a change in X results in change in Y. And this change of Y, we are sure that this change of Y is solely due to, is a direct consequence of the change in X. So X cause Y. In contrast, if we say X is correlated with Y, okay, that measures, this correlation measures the association between X and Y. And if there's a causality from X to Y, then we can say that there's a correlation between X and Y. However, if there's a correlation between X and Y, we cannot say that there's a causality between X and Y, from X to Y. Okay, so I hope you are clear about this distinction. Okay, Lubin causal model. So let Y represents an outcome, whatever outcome we want to measure. For example, like a class size examples, the outcome could be students' final exam scores. And D represents a treatment status. D only take two values, 0 and 1. If it's 0, it's not treated. If it's 1, it is treated. The unit is treated. So D is a dummy variable or indicator variables. In I, the subscript I will index units. So Y0I is the potential outcome of unit I if it is not treated, if it has a treatment status DI is equal to 0. Y1I, it is a potential outcome of unit I if it is treated. Okay, these two potential outcomes. Right, okay, so we can calculate the individual treatment effect, tau I, the treatment effect to unit I as the difference between these two potential outcomes. Tau I is equal to Y1I, potential outcome if treated, minus Y0I, potential outcome if not treated. Unfortunately, tau I is not observed. We cannot compute this tau I. This is because if unit I is treated, then we observe Y1I. However, Y0I is unobserved. If instead unit I is not treated, then we observe Y0I. But Y1I is unobserved. So always, in either situation, always we have the counterfactual unobserved. So we cannot estimate tau I. Typically, we would be just happy to estimate the average treatment effect, or sometimes it could be average other quantities such as average treatment effect on the treated. So we typically are interested to know average treatment effect, is the expectation of the tau I. So which is expected value of difference between potential outcome, the two potential outcomes, and is equal to expected y1i minus expected value of y0i, and this equality is because of linearity of the expectation operation. So we are kind of in a dilemma. If a unit is treated, we don't observe the untreated potential outcome. If instead a unit is untreated, we don't observe the potential outcome of treated. So counterfactual is always unobserved. So in order to us to estimate this, the key trick here is that we need to find a way to estimate this counterfactual. So later on, we are going to have different designs that allows us to estimate these counterfactuals. And also note that the observed outcome is called yi. Observed outcome unit y will be equal to y1i times di plus y0i times 1 minus di. So if di is equal to 1 is treated unit, then we get y1i times 1 plus y0i times 1 minus 1, which is 0. 0 times everything disappeared. So we get y1i. The observed outcome is y1i. If instead di is equal to 0, then the observed outcome yi is equal to 0 times y1i, which is 0. We can ignore that. Plus y0i, 1 minus 0. So this is 1. So the observed outcome is y0i. And we can rearrange the terms. So this multiply inside, we get a y0i minus y0i di. And we have terms y1i times di plus. So we can combine these two terms. So we get a y0i is here, and the difference y1i minus y0i times di. And you should know that this is tau I. Okay, that's the individual treatment effect. Okay, this is Rubin's causal models. And our task, we want to estimate the treatment effect or average treatment effect. The dilemma we have is that counterfactual always unobserved. So the trick is that we need to find a way to estimate the counterfactuals. Okay, let's look at first design. Randomization design. Suppose we have the degree of freedom to conduct an experiment. So in the experiment, we randomly assign the treatment status. For example, in the fertilizer experiment we see previously, we randomly choose which plot to apply fertilizer. So in these cases, this randomization means that DI, the treatment status, is independent of these two potential outcomes. Okay, Okay, so there's a concept about independency. This is concept of probability knowledge. Loosely, we can understand this, that okay, if DI is independent of y1i, that means if we condition expected value of y1i condition on DI is equal to 0, suppose, then that's the same as expected value of y1i. So you see that when we condition on DI equal to 0, it does not give us much information, additional information, because these two random value of DI and y1i, they are independent. And similarly, condition DI is equal to 1, that's the same. And also for y0i, the potential outcome of untreated. Okay, so this randomization allows us to estimate the counterfactuals. Okay, so this the average treatment effect is equal to this. That's the definition. Okay, and now we want to have this and this. We want to estimate this. So remember. So now we can replace these terms by these terms. Why do we want to do so? Because if di is equal to 1, we observe the potential outcome, which is the actual outcome. Okay, so this, if di is equal to 1, condition on this, then y1i is actually equal to yi because we observe this outcome. Similarly, we replace this expected value of y0i by this conditional expectation. And why do so? Because condition on di equal to 0, we observe the potential outcome, which is equal to yi. So that's where the second equality is. So now we kind of operationalize the estimate of this average treatment effect, because now we observe the data, we observe the outcome. Now we move from the potential outcome to the actual outcome. So the average outcome is equal to this. That's the formula we can estimate because we have data now. And why we can do so is because of randomization means that di is independent of these two potential outcomes. So we estimate this one, the first term's expected value of yi conditional on di by its average, sample average. So this is the sum of all from observation 1 to n. Some of these observations will have di equal to 1, the other will have di equal to 0. So this yi, if di is equal to 0, yi di is behind 0. So with sum 0 doesn't matter. Okay, so this sum is the sum of y over di equal to 1 and divided by its number of treated units. So this is estimate of E expected value y conditional on di equal to 1. Similarly, this is the estimated version of the expected value of yi conditional on di equal to 0. And the difference of them is the average treatment effect. I hope you are convinced that this is the natural estimator. We already saw this in the previous videos. So, and this is equivalent to regressing yi against the di. So remember, including a di, a dummy variable, or indicator variable, into the regression model, we allow for the intercept to be different. So this is kind of difference estimator. So we know that yi, the observed outcome, is comes from two potential outcomes. Okay, potential outcome of potential untreated outcome, potential treated outcome, and this is a treatment effect, individual treatment effect. So given this, let's take conditional expectation of yi conditional on di. Okay, and now you want to make yourself familiar with this conditional operation of conditional expectation operation. So it's a linear operation. So we get this, the first term come from here, then the second terms. Okay, we are conditional on di, and note that di, because of randomization, di is independent of y0i. So this means that this expected value is equal to expected value of y0i. So this does not depend on di. And that's the first term. Second terms. So we are conditional on di. So when we condition a particularly random variable, we can treat this random variable as a constant. So let's prove it out. Okay, prove this out. It's a constant. Then we get this one. So these terms. Okay, again, now di is independent of y1i, y0i. So this conditional expectation is just equal to expectation, and that's by the definition is our average treatment effect. So we get this regression model beta 0 plus tau di. So from here we can specify a regression model yi is equal to beta 0 plus tau di plus ei. So this is a difference estimators. Essentially comparing the treated units with the control units, and we can do so because we have these randomizations. Okay. Second, difference and differences design. Suppose the situation is that the treatment or the intervention, the policy, the program is implemented at a particular time 0. Before T0, all units are untreated. After T0, some units are treated while the others are not. So now we have a time dimensions in our setup. So let F0 to be the set of units, represent the set of units that has never been treated. And similarly, F1 be the set of units that are treated after T0. So we are going to call F1 group of treated units, F0 group of control unit. And potential outcome. So now we are going to have index IT, subscript IT, because we have time dimension in the design now. So Y0 IT is the potential outcome of unit I in time t if not treated. Similarly, Y1 IT is the potential outcome of unit I in time t if treated. And DIT is dummy variable if unit I in time t is treated, and 0 if not. We don't need this. So note that we can actually write, or typically is helpful to write this dummy variable treatment status as interaction terms of two indicator variables. So DIT is DTI times DPT. So DTI is taking 1 if it is in a treatment group in F1, 0 if it is an untreated group or control group. So this does not vary from time. There's no time variation. Second dummy variable dpt equal to 1 if it is post treatment period. If time is after T0. So we decomposed. We write this treatment status indicator as interaction of two dummy variables. One vary across the group but do not vary across time. The other vary across time but do not vary across the groups. Similarly, the individual treatment effect, which is unobserved, is the potential outcome of treated minus potential outcome of untreated. And the observed outcome, which we call it YIT, comes from, if it is untreated, then it's Y0IT. If it is treated, then we need to add a treatment effect in it, which is tau IT times DIT. And bear in mind that we have data of YIT, that's the observed outcome. The actual outcome is observed. Let's take conditional expectation of YIT conditional on these two DTI and DPT, these two dummy variables. So first terms is this. Second terms, we know that this Y1IT minus Y0IT is tau IT. So we write this tau IT. And let's look at second term first. So E tau it, so we have tau it dit time conditional dti dpt. So little dit is the dti times dpt. So we condition this. We know these two dti and dpt. That means we know dit. So we can treat this as a constant. We can pull it out and write it as the interaction of these two dti times dpt. And then we have these terms inside. That's the average treatment effect. Now we are going to use what is called conditional independency assumption. Again, we need this y1 it minus y0 it, the individual treatment effect, conditional on dti dpt is equal to this unconditional one. So this, we need this conditional independence of treatment assignment. Okay, this is also needed. You can loosely think that we want the policy implementation time to be exogenous. The selection of treatment group to be exogenous. Otherwise, if not, then we end up in having what is called selection bias. Okay, so given these conditional independency assumptions, we can ignore this condition. Okay, so this will be equal to E tau it, and which is tau. So we have this the second terms we know that is equal to tau times dti times dpt. Okay, the first term is, we assume that it's a linear function of the two dti and dpt. So given this, we can specify a regression model yit is equal to beta 0 plus beta 1 dti, beta 2 dpt, plus tau dti times the interaction terms. And the coefficient of these interaction terms captures the average treatment effect. And in my specification here, I do not include any control variables. So I'm implicitly assuming that everything else are controlled, are held constant. If not, you need to include these additional control variables. Say maybe you add beta 3 x prime beta 3. So x prime beta 3. So it could be a vector of other control variables. Okay, so now we have these models, and this is called the difference and differences design. Why? Okay, let's look at conditional, the expected value of y, conditional dt and dp. Okay, we can separate into 4 possible situations. First is before the policy and after the policy, and control units and control group and treated group. If it is control unit, which means dti is equal to 0, before policy, dpt is equal to 0, so this is equal to 0, this is equal to 0, the interaction term is equal to 0. So, and we are looking at conditional expectation, so this is drop, this is equal to conditional expectation is equal to 0, so we get beta 0. Okay, after policy, then now dpt is equal to 1, and the interaction term continues to be 0, so because of the ti is 0, so we got beta 0 plus beta 2. So that's this. Similarly, for treated dTi is equal to 1. So now this is equal to 1. And before policy, this is 0. So this will be 0. So we get beta 0 plus beta 1. And for treated group after the policy, so all these dummy variables equal to 1. So we get beta 0 plus beta 1 plus beta 2 plus tau. Okay. So let's compare the difference between policy, before policy. So the difference of these two outcomes between treated group, which is beta 1, is due to clearly is not due to the policy because we haven't implemented the policy yet. It's due to any other unobserved factors. Okay, due to unobserved factors. And after policy, let's compare the difference, which is beta 0 plus beta 1 plus beta 2 plus tau minus beta 0 plus beta 1. So we get beta 1 plus tau. So this is due to both policy and other unobserved factors. Okay. Then, so now we have two difference before policy difference, after policy difference. Then if the effect of these unobserved factors are constant over time, then we can take a further difference, secondary difference. So this is why it's called difference and differences. So which is beta 1 plus tau minus beta 1, which is tau. And this captures the treatment effect, average treatment effect of this policy. Okay, that's why it's called DID. And graphically, we can present this before policy, so before the interventions. This is treated unit, this is control unit, and there's already a difference here. And this is due to any unobserved factors other than the policy. After that, after the policy, we see that the total difference is this. One component of it is due to these other unobserved factors, which we can estimate it from the pre-policy difference. Okay, then this difference is the treatment effect. Essentially, when we are doing source, okay, say this treated units post policy, it is counterfactual, should be this dashed line, dotted line. However, it is unobserved. Fortunately, we have this to serve as an estimate of counterfactual. So we are using, so to estimate the counterfactual for the treated units, we are actually using the fact that before policy, we have some units that exhibit similar trend before the policy. We can use them as a kind of estimate for the counterfactuals. And I hope you see that in doing so for this estimate to correctly pick up the average treatment effect, we need to have this parallel trend. Before the policy, these two outcomes, the outcome for treated and control group, they need to exhibit the same trend before policy in the outcomes. And this is called parallel trend assumptions for the DID estimator to pick up the average treatment effect correctly. We need the outcomes of treated and control units before the policy to exhibit the same trend. And we can test for this. We can restrict regression to before the policy, and there shouldn't be a significant difference between the treated and control unit. Okay, that's the second DID design. Third, regression discontinuity design. So random assignment of treatment status can be difficult to achieve. And sometimes the assignment treatment status follows a deterministic rules. For example, say we want to evaluate a program of giving students laptops, whether this increase their performance, academic performance or not. Then the assignment rule, the treatment status assignment rule says that, okay, students receiving 75% or higher scores in the midterm exams will receive a laptop in the award. Okay. In such cases, this treatment assignment is not random. Instead, it's deterministic. And in such cases, RDD, research discontinuity design, arises. So here, let's suppose X determines, well, which in our example is X is the midterm exam score, determines whether unit I is assigned to treatment or not. So DI is equal to 1 if XI is bigger than C. So we know this C. X is called a forcing variable. And this design is kind of sharp regression discontinuity design. We want to know that here conditional and dependency assumption automatically satisfied. So the potential outcome Y1I DI is and XI will be exactly the same as Y1I conditional XI, because DI is actually itself a function of XI, and similarly for Y0I. So this is automatically satisfied. However, there's no overlapping. That means if we observe, if an observation is treated, so for, okay, there's no, frequently we will need this implicitly this overlapping assumption. That means that for xi equal to particularly same, say, particular values, say 60%, then we have positive probability of observing that is treated, di equal to 1, and positive probability that is control. Okay. If not, say we all observe di equal to 1, say if xi is the midterm score is 60%, actually according to our rules, di is actually will be 0. So we don't observe any situation, any outcome where di equal to 1, actual outcome. Okay, so that's what it means by overlapping. Okay, given value of x, we need some units has di equal to 1, the other units has di equal to 0. Okay, but in our regression discontinuity designs, there's no overlapping. Okay, so the actual outcome is a function of, comes from a potential outcome. Okay, and the treatment effect is the difference. Individual treatment effect is the difference between the potential outcome of treated and the potential outcome of untreated. And this again is unidentified because we don't observe the counterfactuals. However, here the idea is that in the neighborhood, in a small region around the cutoff point, those treated should be very similar to those controls. Again, now here we are trying to estimate the counterfactuals, but given our particular design here, it should be reasonable to assume that in a small neighborhood close to the cutoff point, those who are treated, those who are awarded the computer, should be very similar to those who are not. Okay, so close to the cutoff, we have something similar to random assignment. Okay, therefore we can estimate the treatment effect around the cutoff. So now the estimation of treatment effect is actually local. Okay, around the cutoff, we call it tau c. So So is the expected value of these two potential outcomes around conditional on the cutoff point. Okay. So this is equal to these two expected value. So we need to estimate them. Graphically, so this is a cutoff point. So we are going to take a neighborhood. We certainly want, so this neighborhood, we can choose a bandwidth, okay, focus within this neighborhood. Then these are the control, these are treated, and we can reasonably argue that within this band in this neighborhood, this assignment of the treatment status is random and compare difference. So in particular, we will be, let's say we can fit the line across this point and then fit the line across this point. Then the treatment effect at this point will be the difference here. Okay. So that's a graphical illustration of this regression discontinuity design. Actually, it's a sharp design here. All right, so what we can do is for the units below the cutoff, we run a regression, okay, regress outcome, the actual outcome, against xi minus c. So we want to rather than using xi, we want to using xi minus c. So at the cutoff, this where xi is equal to c, then we get this value will be 0 at the cutoff. Okay. And similarly, for units above the cutoff, we estimate a regression model of this y is alpha 1 plus beta 1 times xi minus c plus any other terms. And if we got the estimate, we use these two samples. Run the estimation, we have estimate alpha 0 hat and alpha 1 hat. The average treatment effect at the cutoff, the local average treatment effect is the difference between alpha 1 hat and alpha 0 hat. To see this, so for the control y hat, I is equal, or expected value, let's say expected value, yi for the control is actually equal to alpha 0 plus beta 0 hat plus xi. Now xi is equal, we want the xi is equal to c. Xi is equal to c, then c minus is 0, so it drops out. And similarly for the treatment is equal to alpha 1 hat. Difference then tells us the average treatment effect at the cutoff. Okay, so now we run regression across these two groups, above the cutoff, below the cutoff. We can pull them together, okay, using indicator. So remember we have this di is equal to 1 and 0 above cutoff, 1 above cutoff, 0 below cutoff. So we can combine this, allow the intercept to be different, and also allowed include the interaction terms to allow for the slope to be different. Okay, and this tau c pick up the coefficients of the coefficients of the di pick up the average treatment effect at the cutoff. Okay, remember at the cutoff this term is 0, so that's why gamma does not contribute to the estimate. Okay, there are some additional considerations in RDD. For example, you might want to restrict the samples to data within distance h. H is a bandwidth of the cutoff point, and to check, and you might use different h to check the robustness of your estimation. And sometimes the relationship between y and x could be nonlinear. Y is equal to fx. So now you might want to using higher order polynomial of x. So for example, xi minus c squared or xi minus c to the power 3 in your regression. Okay, and this regression discontinuity design could be fuzzy. So the assignment rule is that, okay, it's not deterministic. It could be, there's a probability that even if the midterm score is higher than 75%, is still assigned to the control. The student is still not given a laptop. Okay, in these cases, there's a fuzzy. It is called fuzzy regression discontinuity design. Okay, these are some basic of the policy evaluation. So the key difficulty is that counterfactual is always unobserved. To solve this problem, we want to find a way to estimate the counterfactual. Okay, that's a key trick. So we have different designs, randomization and experiment. This allows us to estimate. The randomization is a source of identification. It allows us to estimate the counterfactual. Through the randomization, the treatment status is independent of potential outcomes. Okay, by design. We also have DID design. Now the counterfactual comes from the untreated units that expect the same trend pre-policy. Okay, so we using this DID to difference out the difference, the difference of this observed outcome between these two groups post-policy. The difference post-policy with the difference pre-policy. Okay, to difference out any influence from unobserved factors. Okay, and the RDD counterfactual comes from the untreated units that is close to the cutoff point. Okay, so and when we focus our attention to a small neighborhood around the cutoff point, we're able to treat that. We're able to pretend that this treatment assignment is random. Okay, that's the essence of RDD design.